Elements. This podcast is to help you solve the last minute must do problems. Because I do not have FaceTime with you, I am hoping that through this podcast you will get a good understanding of how to do these problems and some of the commonly made mistakes and some of the things to keep in mind. So the first problem here deals with um, this this problem is based on calculating empirical formula from combustion data. Let's read the problem first. Problem says when 1.125 grams of liquid hydrocarbon CXHY was burned in oxygen, 3.447 grams of carbon dioxide 3.447 grams of carbon dioxide and 1.647 grams of water were produced. The molar mass of compound was found to be 86.2 grams per mole. What is the empirical formula and the molecular formula? So as you recall, the empirical formula refers to smallest whole number ratio of moles, and because it's a hydrocarbon made up of just carbon and hydrogen, if we can figure out the moles of carbon and moles of hydrogen, then we can calculate its empirical formula. And that's a pretty simple problem. A little deviation of similar problems, if you recall from chapter 2, is when you have a organic compound that has carbon, hydrogen, and oxygen. And typically in those problems, they'll give you total mass of compound which has carbon, hydrogen, and oxygen. They will give you mass of carbon dioxide and they'll give you mass of water. So using mass of carbon dioxide, you can get mass of carbon. Using mass of water, you can get mass of hydrogen. And if you add up both the masses and subtract from total, then you can get mass of oxygen. And once you have all the three masses, you can convert them to moles. So that's a little variation of this type of problem. I just wanted to remind you of that. This problem, however, just deals with carbon and hydrogen. So what you're going to do is you're going to try and figure out moles of carbon from mass of carbon dioxide. And you know 44 grams of carbon dioxide is 1 mole of carbon dioxide, and in 1 mole of carbon dioxide you have 1 mole of carbon. And if you follow this process, then this gives you 0.078 moles of carbon. Similarly, starting with water, you can figure out moles of hydrogen. You know 18.02 grams of water make 1 mole of water, and in 1 mole of water you have 2 moles of hydrogen, and that gets you 2.34 moles of hydrogen. And now to figure out empirical formula, you divide each by the smallest number of moles, which is 0.078. And this is a step that kids oftentimes forget. So I would like to remind you, once you figure out the moles of individual elements, you must divide them by smallest number of moles. And in this case, you get the ratio of carbon to hydrogen as 1 to, I'm sorry, I wrote this number wrong. This number is 0.183 moles, and when you divide it by 0.078 you get 2.34 moles here. And since it's a third fraction and you need a small whole number ratio, you multiply it by 3, and the empirical formula hence comes out to be C3H7. And its molecular formula will be empirical formula times a small whole number ratio, and this N can be calculated by molar mass divided by empirical formula mass, which is the mass of the empirical formula. So 12 times 3 plus 7 gives you about 43 grams per mole, which gives you this factor of about 2. So if you take the empirical formula and times it 2, you get the molecular formula. So its molecular formula will be C6H14. And that is problem number 1. I would like to remind you again, the overall process goes like this. In empirical formula from combustion data, from mass of carbon dioxide, you get moles of carbon. From mass of water, you got moles of hydrogen, and then you divide both the moles by smallest moles. And if you get a whole number, then that's your empirical formula. If you get a ratio, you got to multiply it to get a whole number. And that is the empirical formula from combustion data. And that was problem number 1. That's pretty simple. Now let's look at problem number 2. Problem number 2 says, what is the pH of a solution when 90 mils of 0.1 molarity NaOH has been added to 100 mils of 0.1 molarity acetic acid? Anytime you have an acid and a base mixed together and you're asked to calculate its pH, you must start with a neutralization or ICF chart. If you recall, ICF chart is written in moles and not molarity. And you'll write the neutralization reaction on top, which is NaOH. So you can write net ionic equation because Na is a spectator ion, it will get cancelled. You can just write OH minus. And acetic acid, it being a weak acid, you write the whole acid and not dissociated. When they neutralize, they form H2O plus acetate ion. And you don't care about H2O. And if you multiply mils times molarity, you get OH minuses moles. And OH minus moles are 0.00, let me just get rid of this here, 0.009 moles. And acetic acid is 0.01 moles, and initially you have 0 acetate moles, and you would want to subtract smallest number of moles, which is 0.009, and you subtract 0.009 moles and 0.009 moles form here. So finally you have no more hydroxide left. You have 0.001 moles of acetic acid left, and you form 0.009 moles of acetate. Now, if in a solution you have acetic acid and acetate both, acetic acid and acetate, that makes an acidic buffer. And when you have a buffer, you can figure out its pH by either using Henderson-Hasselbalch equation or using ice chart. But before you can do either, excuse me, you will divide both the moles by total volume, which will be 90 plus 100, 190 mils or 0.190 liters, because ice chart or Henderson-Hasselbalch equation is for molarity. So I like to go ice chart way. You can use Henderson-Hasselbalch equation as well. If you use ice chart, then the equilibrium will be for acetic acid making H plus and acetate ion, and you write the amount. When you divide 0.001 by 0.190, you get 0.0053 molarity of this, 0 molarity of this, and when you divide 0.009 by 0.190, you get 0.047 molarity of this. And then you go minus x, x and x. So at equilibrium, you have 0.0053 minus x, x, and 0.047 plus x. And when you write the Ka expression, it will be x times 0.047. We'll ignore the plus x divided by 0.0053. And Ka value here is 1.8 times 10 power negative 5 is equal to x times 0.047 divided by 0.0053. That gives you a value of x as 2.03 times 10 power negative 6 molarity. And when you negative log x, which will be the pH, because x is for H plus ion concentration, pH comes out to be 5.69 or 5.70, and that is the answer. So whenever you have an acid and a base mixed in a solution, before you can determine its pH, you need to figure out what are the players remaining after neutralization. Hence, first you must make a neutralization chart, which is made in moles, to see after neutralization what are the players in the solution that will determine the pH of solution. If in the same problem, after neutralization chart, all the acetic acid was gone and only hydroxide was remaining, then you did not need to make ice chart. You could just negative log molarity of OH minus, and that will give you POH, because OH minus is a strong base. But because after neutralization all the OH minus was gone and acetic acid and acetate were left, then the pH is determined by writing the ice chart. So just wanted to bring that to your attention. So that's question number 2. Question number 3 says, what is the pH of a solution at the equivalence point in a titration of 100 ml of 0.1 molar ammonia with 0.100 molarity HCl? The first thing you need to know, again, when there is ammonia and HCl mixed together, it will undergo neutralization. So before you can determine the pH, you need to see after neutralization what are the players that will set the pH. So let's write the ICF chart, and it is written in moles. Remember, I write it again and again so that you remember that. And ammonia and HCl, then Cl minus is a spectator ion. We don't need to write that. It goes one way and it neutralizes to form ammonium. How many moles of ammonia do we have? We have 0.1 molarity times 100 mils, or 0.01 moles. And because it's at equivalence point, and because ammonia and HCl react in a 1:1 mole ratio, if it is 0.1 molarity HCl reacting with 0.1 molarity ammonia, we can assume that it is 100 mils of HCl as well. So we have 0.01 moles of H plus as well, and initially there are no moles of ammonium. Change will be 0.01 moles minus 0.01 plus 0.01. So after the neutralization, you have no ammonia, no H plus, and 0.01 moles of ammonium. So what is setting the equilibrium in the solution is actually ammonium ions hydrolysis. And you know, when ammonium hydrolyzes, because it has extra H plus, it acts as a proton donor or a weak acid, and it makes H3O plus plus ammonia. And because it's decreasing the pH or making the solution acidic, we will write a Ka expression eventually for this, and we'll write a ice chart. But before we can take the moles, we have to change it to molarity, and the total volume is 0.200 liters. So the molarity here comes out to be 0.05 molarity. So here we start with 0.05 molarity of ammonium. Pure liquids are not included, so we'll put X's here, and this is 0 and 0 initially, then minus X, X and X, and at equilibrium we have 0.05 minus X, X and X, and we write Ka expression. Again, we write Ka expression because ammonium's hydrolysis, NH4 plus's hydrolysis, is making the solution acidic. And then you write X square over 0.05 minus X. And they have given you Kb for ammonia, but you're writing Ka expression. So it'll be 1 times 10 power negative 14 divided by 1.8 times 10 power negative 5 is equal to X square over 0.05. We can ignore the X. And then when you solve for X, you get 5.24 times 10 power negative 6 molarity, and the pH comes out to be negative log of X, which is 5.28. Remember guys, at equivalence point, you have no more acid or base left to determine the pH. What determines the pH at equivalence point is the salt hydrolysis. So you must see what is your salt and does it make the solution acidic or basic. Should you be writing a Ka or Kb expression? So that is question number 3. Now for question number 4, you will need a little bit of information that wasn't given to you. You will need Ka of HOCl, which is 3.5 times 10 power negative 8. Now let's read this problem. This problem says sodium hypochlorite NaOCl is the active ingredient in laundry bleach. Typically, bleach contains 5% of this salt by mass. So mass over mass is 5%. and this is equal to 0.67 molarity solution. And they say compute concentration of all and its pH and the molarities. So first, let's write if it is OCl minus solution, its hydrolysis, because it's an aqueous solution, will produce what? It will produce HOCl plus OH minus. So our pH should be slightly basic. And then we'll write a Kb expression. Now OCl minus's molarity initially is 0.67 molarity. We are not concerned about water because it's pure liquid. We set up a ice chart, and HOCl initially 0 0, then minus x, x, and x, and at equilibrium we have 0.67 minus x, x, and x, and we write Kb expression as x square over 0.67 minus x. And because we are given Ka for conjugate acid and bases, Ka times Kb is Kw, we'll write Kb as 1 times 10 power negative 14 over Ka, which is 3.5 times 10 power negative 8, is equal to x square over 0.67. We can ignore the x. So x's value is 4.37 times 10 power negative 4 molarity, and this x is equal to molarity of OH minus. And if you do that, then there is all other values like POH and Na plus, H3O plus, you can calculate all of those. So as long as this value comes out to be the same 4.1 times 10 power negative 4, you're good to go. So it's pretty close. I think they used a different Ka value. So I think it's some places it says 3.6, some places it says 3.5, but that is the way to go. And then once you calculate OH minus, you know H plus times OH minus is equal to 1 times 10 power negative 14. So because you've calculated OH minus already, you can calculate H plus that way. And if OH minus is x, then HOCl is x as well. So HOCl's molarity will be same as OH minus, and OCl minus's molarity will be 0.67 minus this value. And then if you negative log x, you get POH. So 14 minus POH will be pH. And that's how you do problem number 4. Now problem number 5 is based on redox. Don't be scared looking at the length of the problem. They are just giving you the data that you need to be able to solve this problem. So let's look at redox problem. This problem says the electrolysis of an aqueous solution of Ki. So Ki, aqueous solution, is electrolyzed, and it makes hydrogen gas at cathode, and it makes iodine at anode. And then it says a sample of 80 milliliters of 0.150 molar Ki was electrolyzed for 3 minutes using a constant current. They don't tell you how much current they passed. At the end of this time, the iodine produced was titrated against 0.225 molar sodium thiosulfate. So whatever iodine was produced was titrated against sodium thiosulfate via this equation. And it took 37.3 mils of the sodium thiosulfate, that was 0.225 molarity, to reach the equivalence point. Part A asks you how many moles of iodine were produced. Now if you look at this balance reaction, you know at equivalence point 1 mole of iodine is equal to 2 moles of S2O3 2 minus. How do you know that? You know that by looking at the mole ratios of the balanced equation here. So 2 times, and how do we get moles of S2O3? Molarity times volume. So 2 times, how much is molarity? 0.225 molar times 0.0373 liters, and that gives you the value of I as 0.0041 moles, or 4.1 times 10 power negative 3 moles. Let me just check the answer. Yes, or 42 if you, depending on what place a decimal you go to. So that's how you do part A. Let me actually create some more space here. Okay, back to the problem. Part B asks you, the hydrogen gas produced at cathode during the electrolysis was collected over water at 25 degrees at a total pressure of 752 milliliters of mercury. Let me just erase this part A so we can actually see the problem, so you don't have to scroll down. I'll erase part A for you, and then we do part B right here. So the hydrogen gas that was produced was collected over water. So when you collect gas over water, remember water vapor sneaks in there, and total pressure is 752 millimeters of mercury. So pressure of gas will be P total minus P of water. P total is 752 millimeters mercury, and pressure of water is 24 millimeters mercury. So pressure of gas is 728 millimeters mercury. And you know that this gas is collected under non-standard condition. So to get the volume, it'll be nRT over V. And how do you get moles of hydrogen? You know moles of iodine. You've calculated that as 0.0042 moles in part A. Now, you know that iodine, when it is formed, it's formed from iodide being oxidized, meaning losing 2 electrons and then forming iodine. And this happens at anode. So the current that flowed through this released 1 mole of iodine when 2 moles of electrons were passed. Now, to figure out how much of hydrogen moles will be produced, you got to look at the reaction through which hydrogen is being formed. So hydrogen is formed from water, if you remember, at cathode through this reaction. 2H2O plus 2 electron gives you H2 plus 2OH minus. So to make 1 mole of hydrogen, you need 2 moles of electrons. So you can look at it this way, that to make 1 mole of iodine, 2 moles of electrons were released, and you need 2 moles of electrons to make 1 mole of hydrogen. So moles of hydrogen formed will be equal to moles of iodine. That's one way of doing it. And in that case, moles of hydrogen will be 0.0042 moles. This is one way of thinking. Other way of thinking could be, you can think in terms of Faradays. You know, 0.0042 moles of iodine were formed when, and to make 1 mole of iodine, you need 2 moles of electron, and 1 mole of electron is 1 Faraday, and 1 Faraday is 96500 coulomb, and you can figure out how many coulomb of charge was used. And you can use the same coulomb of charge and say that 96500 coulomb is 1 Faraday, and 1 Faraday is 1 mole of electron, and you need 2 moles of electron to make 1 mole of hydrogen, because you know that the reduction reaction of water, and this way you can get moles of hydrogen. Ultimately, if you take a good look at it, you're canceling out everything. It's the same ratio. Hence, the moles of hydrogen are equal to moles of iodine. So let's go back to our problem, and we have all the data here now. To calculate volume, we have moles of hydrogen, which is 0.0042 moles of hydrogen. R will be 0.0821 liter atmosphere per Kelvin mole. Temperature will be 298 Kelvin because it is at 25 degrees Celsius. And the volume, I'm sorry, This is the pressure, not the volume here. And the pressure of the gas collected, dry gas, was 728 millimeters mercury divided by 760 millimeters mercury. And when you solve it, you get the volume of hydrogen gas as 0.107 liters. 0.107 liters. And this is a great example of a problem where redox, gases, stoichiometry, everything is combined in one part. Then for part let's go a little bit up here. And then for part C of the reaction, it says write the half equation that occurs at anode. And you know anox, red cat. So what happens at anode is oxidation, and you know iodide is being oxidized into iodine plus 2 electrons. So that will be the reaction at anode. And then they say calculate the current used in this electrolysis, and that's where we'll do something what we've done in part B. You can say that you made 0.0042 moles of iodine, and you know, I will erase this so you don't get confused. You know, to make 1 mole of iodine, you need 2 moles of electron, and 1 mole of electron is 1 Faraday, and 1 Faraday is 96500 coulombs. And this way, you'll calculate the coulomb, and I actually haven't done this calculation, so let me quickly punch in the number, 0.0042 times 2 times 96500, and that gives you 810.6 coulombs. And you know Q is equal to IT, and Q's value is 8.10. Q's value is 8.10.6. So if you divide that by 3, which is the amps, you get so you're not, that's 3 amps is, it's for 3 minutes, and you have to figure out the amps, and you know your coulomb is 810.6. So coulombs is 810.6 coulombs, and you have to calculate I, which you don't know, and T time needs to be in seconds, but it is 3 minutes. So if you convert that to seconds, 3 times 60, and divide 810.6 by 180, you'll get 4.50 amperes, and that is your answer there. I am not able to write, my wireless tablet just stopped working for some reason, so just on time. Hopefully guys you will find this helpful, and thank you for listening, and all the best of effort on your AP exam. I know you'll do well. Thank you.